All right, so we got some specifics on how nucleophile and leaving group impact the rate of an SN2 reaction, but we haven't really talked about the orbitals in this process. And this brings us to page 7 of the notes, and it's something that's not really covered very well in the textbook. So it's really important that you guys check this out. So on the top of that page, it says, how does an SN2 reaction happen? And it gives some specifics about something called an antibonding orbital. So if we're looking at a molecule like CH3I, what does that look like? Well, that's an sp3 hybridized carbon, so it's got a tetrahedral geometry. So we'll put the C and the I there. We'll put the H here. We'll do another H here and another H here. And we're actually going to talk pretty extensively about this C-I bond. So I'm just going to put the C and the I there for now. But what it says in these bullet points on this page is that in molecules there are bonding orbitals, and there's also something called antibonding orbitals. Bonding orbitals are where the electrons are located to make stable bonds. So in the halogen-carbon bond, this orbital is the sigma orbital. So again, how does that occur? Well, we have an sp3 hybridized orbital here, bonding to the iodide, and we'll just draw that as a kind of a straight line, but I'm just showing this as the bonding orbital. This is the C-sp3 sigma orbital. So this is the bonding orbital. The bonding orbital. So in the halogen-carbon bond, this is the sigma orbital, located between the halogen and the carbon atom. Next bullet point says antibonding orbitals are where electron density can be added to weaken a bond. So in the halogen-carbon bond, this orbital is called, so this is the sigma orbital, In the halogen-carbon bond, this orbital is called the sigma star, and it's located on the back face of this bond, and it's a pretty small little area. So we're just going to make it look like that. Remember, sp3 orbitals in general look like this. So this is the bonding side, and this is the anti-bonding side. We'll just put anti-B for anti-bonding. So this is the bonding, this is the sigma star anti-bonding orbital. So this is where the nucleophile will add electron density to make a new bond. So in an SN2 reaction, the nucleophile adds electron density to the sigma star to make and break, because it's making the nucleophile bond, right? So you have the nucleophile here. It's making the nucleophile carbon bond, and it's breaking the carbon iodide bond. So it's making and breaking the bond. So the nucleophile adds electron to the sigma star to break bonds. So that's what the deal with this sigma star orbital. It's a small orbital on the back face of the carbon-halogen bond, and it is where the nucleophile adds electron density to break that other bond. So yeah, that's kind of what happens kind of on an orbital level. It's making a new sigma orbital by adding electron density to the sigma star orbital. So that's what's going on with the orbitals. We're going to talk more about that right now. All right, so here's the next question. We have alkyl iodides. We have a nucleophile, and the nucleophile is the same. The leaving group is the same across all 4 of these examples. But the question remains, which reaction would proceed fastest via an SN2 reaction, right? So based on what we just said, the nucleophile has to get to that sigma star antibonding orbital. Take a minute and think about this. Which of these reactions is going to proceed the fastest? How is the nucleophile going to get there? So pause it, generate a hypothesis for yourself. Which one's going to be fastest? And then come back. Okay, you're back. Whatever you said is probably a valid idea, but what it really has to do with is access to sigma star. So can the nucleophile gain access to that antibonding orbital? And remember, that orbital is a small orbital on the back side of the carbon-halogen bond. This first one at the top just has 3 hydrogens around that antibonding orbital. It's going to be really easy for that nucleophile to get there, right? There's not a lot around that sigma star orbital. Once we get from, this we would say is a methyl iodide. This is a primary carbocation. This is a primary a primary alkyl halide. Remember, we classified alkyl halides before, and we said that that alkyl halide type was going to have an impact on the reactions. This is a primary alkyl halide. This is a secondary alkyl halide. And this is a tertiary alkyl halide. So how is that going to impact the reaction rate? Well, with each additional CH3, it's going to be harder for that nucleophile to get to sigma star. Here with the primary one, it still pretty easily can do that. Adding there, it's only really blocked by a single methyl group. But then down here with a secondary one, we have a CH3 here, a CH3 here. Those CH3s are pretty big. They're getting close to blocking that sigma star. It can still get there, but it's challenging. It's hard for the nucleophile to fit into the space blocked by both of those CH3 groups. And it turns out that it can't even get, it's blocked. Once we get to a tertiary alkyl halide, these big old CH3s, having 3 of them right around that sigma star is too much. It's blocked. This last one will do no SN2 reaction because it's too hard for that nucleophile to get to the sigma star orbital. So essentially, what's the fastest reaction of these? The easier that nucleophile can get to the sigma star, the faster the reaction will be. So this is the fastest. And if this one doesn't happen at all, then obviously this is the slowest. So the more open sigma star is, the easier it's going to be to get there. So how do we see that with electrostatic potential maps? Remember, the nucleophile is adding to the partial positive that sigma star has in it because it's a polarized bond. And that's what we have in the note packet right here. We can see that the CH3Br access to that sigma star is really open. The area right behind that bond is just wide open. The H's are really small. But we add a single methyl group there. It still can get there pretty easily, but not super easily. 2 methyl groups, it's even more hindered. And 3 methyl groups, it's actually kind of impossible for that nucleophile to fit in there, even though this figure is kind of showing it happen anyway. It actually can't in reality. And that's what it says right here is increasing steric hindrance. Steric hindrance is the fancy way of saying there's a bunch of stuff around there. It's really hard to get there. Steric hindrance, lots of stuff in the way. So this has the most steric hindrance. We can't get there at all. And this would have the least steric hindrance. There's not a lot in the way. So that's an additional piece that goes into this is can the nucleophile even get to the place that it needs to get to undergo this substitution reaction. So, and we'll find out that this is also going to have stereochemical implications, and that's where we're going next.